Hello everyone. As you have seen in my email, I've decided to have a fully online exam review session. I think this works better for everyone because you will definitely come back to this lecture and watch this online. And if we do a completely online lecture, the quality of the online lecture will be better. Okay, so let's talk about the exam. Exam 2, as you are all aware, is going to be given on April 15th from 5:30 p.m. to 6:45 p.m. Okay, and we'll go over the materials from chapters 4, 5, and 6. Essentially, the flow over airfoils, flow over wings, and compressible flow. Okay. If you're an undergrad student, meaning that if you have registered for EMCH 578, you have to solve 3 questions. If you are a graduate student, meaning that you have registered for EMCH 744, you have to answer 4 questions. An exam is going to have a total of 4 questions, and it's going to be worth 25 points. If you have registered with SDRC, you can reserve a time slot with SDRC and take the exam there, or you can come to class. Okay. You can bring a just one two-sided cheat sheet to class. You do not need to bring tables, and you can use a calculator. Okay. And let's talk about your project as well. Your project, of course, is going to be due exactly next week, so April 17th. This is for the presentation and final report, both of them. Okay. And I will schedule the presentations. Myself, you will have 15 minutes for presentation max. That is presentation plus questions. A total of 15 minutes. And I guess that's it. Please let me know if you have any further questions. Okay, so today we are going to solve a couple of example problems. I guess the rest of the example problems that I wanted to solve. And that will be it. Let's start with homework 1. So, sorry, not sure what this is. Let's start with homework 1. This is, we are going to focus on problem 16 of homework 1. Okay. It is telling us that NACA 2412 has a mean camber line given by this formula. 0.25, 0.8 x over c minus x over c squared. This is for x's between x over c, I'm sorry, between 0 and 0.4. And for the rest of it, we have 0.11, 0.2 plus 0.8 x over c minus x over c squared. This is true for x over c's between 0.4 and 1. Okay, first of all, what is this? This is the mean camber line equation, essentially. Essentially, it is telling us, let's say this is our airfoil. This is showing us what the camber line equation is, right? From 0 to 0.4 of x divided by camber line, we have the first equation. And for the rest of it, we have the second equation. Okay? The reason we use the mean camber line is because we are dealing with thin airfoils. So essentially, the airfoil is the camber line, right? And we are asked to find, using the thin airfoil theory, to calculate the zero lift angle of attack, lift coefficient at angle of attack of 3 degrees, quarter chord moment coefficient, and the location of center of pressure divided by C when angle of attack is 3 degrees. Okay. So if you recall, in our equation, we actually had the derivative. I'm not sure what is going on here. We had the derivative. Let me change the pressure sensitivity. Yep. We had to calculate the derivative of the camber line, so dz dx. This is what we had to calculate, right? And we have two different equations. So before the first one, where x over c is small between 0 and 0.4, dz dx is going to be 0.2 minus 0.5 x over c. And for x over c is between 0.4 and 1, dz dx is going to be 0.0888 minus 0.222 x over c. Okay. If you recall, the equation for zero lift angle of attack was this. Negative 1 over pi integral from 0 to pi, or 0 to c, depending on your coordinate system, dz dx cosine of theta minus 1 d theta. Okay, so this is in Cartesian coordinate system. and this is in polar coordinate system, or cylindrical or spherical, right? So Cartesian polar, which means that we have to convert one to the other, and the conversion equation was like this. So x over c is equals to 1/2 1 minus cosine of theta. So wherever I see x over c, I have to put 1/2 1 minus cosine of theta right here. See one here and another one here, right? So let's redo these equations. dz dx is equals to negative 0.05, and I'm writing the final equation here, plus 0.25 cosine of theta. This is for thetas that are between 0 and 1.3694. How did we get to this equation? So in Cartesian coordinate system is about 0.4. We just say it equal to 1/2 1 minus cosine of theta. That's it. And this is essentially our new theta. Okay. For the second part of this line, the Campbell line, we are going to have negative 0.0223 plus 0.1111 cosine of theta. And here we have theta is between 1.3694 and pi. It's very important to keep in mind that this is in radians, not gradients, not degrees. So it doesn't really matter. You can do degrees if you want, but you have to be consistent everywhere. This is very, very important. Okay. So let's write the zero leaf angle of attack equation. Again, negative 1 over pi, integral from 0 to pi, dz dx, cosine theta minus 1, d theta. Okay? Since we have two different equations, we have to divide this integral into two different integrals. So negative 1 over pi, integral from 0 to 1.3694, negative 0.05, plus, this is the first equation, 0.25 cosine of theta, multiplied by cosine of theta minus 1, plus the second integral, which is 1 from 1.3694 to pi. The second integral is negative 0.0023223 plus 0.11, another one, cosine of theta, multiplied by cosine of theta minus 1, d theta. This is all one line, guys. Okay. Just let's multiply this parenthesis with this and this parenthesis with this and see what we're going to get. We're going to get negative 1 over pi, integral from 0 to 1.3694, 0.05 minus 0.3 cosine of theta plus 0.25 cosine squared of theta d theta, plus the other integral from 1.3694 to pi of 0.0223 minus 13334 cosine of theta plus 0.111 cosine squared of theta d theta. Okay, two integrals. I forgot the bracket here. And you have to make sure in your cheat sheet you include the integral of cosine square of theta, cosine cube dot theta, and integral of cosine of theta, all of these. And I did show you in class where you can find these. You can also Google these. You want to make sure to include these in your cheat sheet. This is very important. Okay. So when you do include these in your cheat sheet, you can see that you will have the integral of all of these different parameters, all of these different integrals, and the final integral is going to be negative 1 over pi 0.005 theta minus 0.3 sine of theta plus 0.25 theta over 2 plus 1/4 sine of 2 theta from 0 to 1.3694 plus, or I guess minus 1 over pi integral of the second one, which is 0.0223 theta plus or minus 1.3334 sine of theta plus 0.111 theta over 2 plus 1/4 sine of 2 theta. This time from 1.3694 to pi. And this is the rest of it, just plug and chug. Again, you have to keep in mind that this is in radians. You have to make sure that you are clear on this on this point specifically. And just plug and chug. Based on what I have in the solutions, we'll end up with negative 0.0726 radians, which is equal to negative 4.1 degrees. And we are, for part B, we are asked to find lift coefficient, which is lift coefficient. Let me actually remind everyone of this. Lift coefficient versus angle of attack. For this special case, we have 0 lift angle of attack as negative 4.6 degrees, and then this is linear up until the stall point. We don't really know where that is, but we assume it is not at 3 degrees. So we want to find the lift coefficient at 3 degrees. Essentially, this is just an equation of the line, and we already know that this lift slope for a thin airfoil is 2 pi. Okay, so using all of this information, CL is going to be, can be found as 2 pi multiplied by alpha minus 0 lift angle of attack. So CL is 2 pi 3 minus 4.16. And there's one thing that you also have to be mindful of, that this is in radians, these are in degrees. So you have to convert these together. How do we convert these together? We can divide 2 pi by 57.3 or multiply the gradients by 57.3. Okay. Plug these numbers in. CL is going to be 0.783. 2. Okay. So for the rest of the problem, I don't think we have the solution to the rest of the problem in the solution manual for some reason, but we can definitely solve this together. So just have to find the equation for zero relief angle, I'm sorry, CM and the quarter chord, which is this equation. So I had to look at it from the lecture notes myself. So Cm at the quarter chord, the moment coefficient at the quarter chord is pi over 4 A2 minus A1, right? What are A2s and A1s? These are the Fourier coefficients. So we have A of n is 2 over pi integral from 0 to pi of dz dx cosine of n theta d theta. Okay, which means that A1 is 2 over pi integral from 0 to pi dz dx cosine of theta d theta, and A2 is 2 over pi integral from 0 to pi dz dx cosine of 2 theta d theta. Okay, what were dz dx? Dz dx, we have already covered everything to polar coordinate. So dz dx is has two different equations. One is negative 0.05 plus 0.25 cosine of theta for thetas between 0 and 13694, and we have dz dx of negative 2.022 3 plus 0.111 cosine of theta 13694 theta and pi. Okay, so for A1 and A2 we just have to plug everything is inside these integrals, and we'll be able to find a solution. The second integral is a bit more difficult because we are dealing with cosine squared of cosine of 2 theta. So what should we do here? We just have to, I guess, do the integrals, do the integrations. Okay, for A1, plug the numbers in. We have 2 over pi integral from 0 to 1.3694 0.05 plus 0.25 cosine of theta multiplied by cosine of theta d theta plus the integral from 1.3694, whatever that is, to pi of negative 0.20223 plus 0.1111 cosine of theta d theta. Okay, if you combine all of these together, we're going to have 1 cosine squared of theta, 1 cosine of theta, 1 cosine squared of theta, 1 cosine of theta, which essentially means that we can find the integrals to be in this format, right? We'll have something. I don't have the final solutions, but I'm going to try to give you the solution. So for this one, we're going to have 0.005, and there's a negative sign here, right? Yes, negative 0.005 sine of theta plus 0.25 theta over 2 plus 1/4 sine of 2 theta. This goes from 0 to 1.3694. All of this multiplied by 2 over pi plus 2 over pi for the second one, which is negative 0.00223 sine of theta. Again, cosine of theta multiplied by this, integral of cosine of theta multiplied by this is sine of theta multiplied by that coefficient, plus 0.111 cosine squared of theta, which integral is pi over 2 plus 1/4 of sine of 2 pi. Goes from 1.3694 to pi. You plug the numbers in. I don't really have a final solution for this because it is not in the solution that I've provided, but you plug the numbers in this and you find the final value for A1. And we want to add another page here. Yep. Okay, so this is for A1. A2 is a bit more difficult because we are dealing with a cosine of 2 theta. So A2, if you plug the things in, is 2 over pi integral from 0 to 1.3694. What was it? It was negative 0.05 plus 2.5 cosine of theta multiplied by cosine of 2 theta d theta. Okay. So, and then I'm not going to write the rest of it. The rest of it is essentially the same thing with different numbers as coefficients. The only thing we don't really have here is the integral of, so we have to take the integral of cosine of 2 theta and the integral of cosine of 2 theta multiplied by cosine of theta. See, cosine of 2 theta multiplied by cosine of theta and cosine of 2 theta itself. You just have to know the solutions to these integrals. The solution to integral of cosine of 2 theta is pretty simple. 2 theta is essentially a theta prime, a different angle, right? So its integral is sine of 2 theta. And then for cosine of 2 theta multiplied by cosine of theta, the final integral is going to be, I think it was sine of theta divided by something plus sine of 3 theta. Sine of theta divided by 2 plus sine of 3 theta divided by 6. Make sure to double check this. I'm just recalling this off of memory. I don't want to do the integrals, but make sure to double check this and include these in your cheat sheets. So when we have the solutions to this, we can find Cm and the quarter chord by just using the equation, which was pi over 4 a2 minus a1. And then for the equation for the center of pressure, I have to go back to lecture notes. Yep, center of pressure. We want the center of pressure divided by the chord length. So the equation is going to become 1 divided by 4, 1 plus pi over CL. We have CL because the angle of attack has not changed. It's still 3 degrees. A1 minus A2. So this is a long problem to solve. So in an exam, you will just be given one part of it. You will be either asked to find the lift coefficient, essentially at a specific angle of attack, which means that you have to find zero lift angle of attack as well, or you will be asked to find the moment coefficient at the quarter chord or the moment coefficient at the leading edge, or CP, X of center of pressure, location of center of pressure. So it is either this or this, not both of them. but it will take a long time. But I guess if you know one, you will know how to solve the other one, so you shouldn't really have any issues with this problem. Let's see. We need to add another page here. Yep. Next problem is problem 17 of homework 1. We are given this is we are asked to find the location of the aerodynamic center, but we didn't really work on it, talk about aerodynamic center that much. I would say the aerodynamic center is a point at which the moment does not change. So based on this fact, you can find the location of the aerodynamic center. This won't be on the exam though. So don't worry about problem 17. Problem 18, we are asked to find the drag coefficient or friction coefficient using the boundary layer formulas. And if you recall, the idea was you have these boundary layers that can start on a flat plate, that can start as laminar boundary layer and transition to turbulent based on your Reynolds number, or they can start as turbulent from the get-go. And we had for friction coefficient, for example, for the fully turbulent case, we had this equation, 0.074 divided by Reynolds number to the power 1/5. Just have to do the calculations and find the friction coefficient. And yeah, this problem is pretty simple. It really depends on whether you are in turbulent region or laminar region. And if you recall, in cases where there's transition happening, we had 3 different steps. The first step was to calculate the laminar, so CF on laminar region using the laminar formulation. So, and then we had to use this equation to find the friction coefficient using the turbulent formulation for all of the plate. So CF and let's call it whole plate, all of the plate, using the turbulent formulation. And then we had to use the turbulent formulation so to calculate the value the turbulent formulation give us in the laminar region, actual laminar region. And then how you calculate the drag coefficient is this. The total drag force is going to be drag of the laminar region, that is calculated using the laminar methodology, drag of the whole region, that is calculated using turbulent form methodology, minus drag of the laminar region, that is calculated using the turbulent methodology. And then we just have to replace this with the equivalent formula that includes the drag coefficient. So CD and laminar multiplied by Q infinity multiplied by S. S here is X critical multiplied by the depth, essentially. And the depth we assumed is 1 plus CD and turbulent and hold all of the plate multiplied by Q infinity, chord length or the whole length of the plate, minus CD for the laminar region, that is calculated by the turbulent methodology, multiplied by Q infinity X critical. Okay, so we have to calculate X critical. And how do we calculate X critical? For the X critical, Reynolds number is going to be equal to 5 times to the power 5. And we're going to put this in this equation, rho v infinity X critical divided by mu, which means that you can find X critical. This is actually how you determine there is transition here as well. Okay, problem 19 focus on the same 19 focus on the same I guess idea, and we are going to move on to the next problem, which is problems from chapter 5. Okay, so chapter 5, the only thing that you will actually see, the only type of problem you will see is that you will be given a distribution of circulation. So let's say this is a top view, front view of a wing. Okay, you will and if you recall, we said that elliptical distribution is the most common distribution, right? You will be given a distribution, a different distribution, and you will be told to compare the different distribution with elliptical distribution. Compare the final I guess if the lifts are equal, if lift is equal, and you have to compare if so this is the type of distribution you will be given. Circulation is a constant gamma naught. This is what you saw in the homework, right? This is the homework problem. This is our circulation distribution. You were told the lifts are equal, lifts of elliptical and parabolic. This is a parabolic distribution, and we wanted to find what is the relationship between this gamma naught of parabolic and gamma naught of elliptical. Okay, then you should do the same thing for the induced velocity. Also, you will be given a distribution. You will be told that lifts are equal. You just have to follow the procedure of problem 1 to get to the final answer. Okay. Moving on, we have already solved problem 2 and 3. We did solve 4, 5, and 6 on Monday. We have solved a couple of shock waves problem as well. Let's actually focus on problem 8 here. Let's see, problem 8. And this will be the last problem we are going to solve. So, problem 8, we are told to consider Mach 4 flow at pressure of 1 atmosphere. So P of the upstream is 1 atmosphere. We wish to slow this flow to subsonic speed through a system of shock waves with a small loss in total, as a small loss in total pressure as possible. Compare the loss in total pressure for the following 3 systems. So first system, a normal shock wave. Second system, 1 oblique shock wave with a deflection angle of 25.3 degrees and 1 normal shock wave. And then the last one is 1 oblique shock wave with a deflection angle of 25.3 degrees, another oblique shock wave with a deflection angle of 20 degrees, and a normal shock wave. And we essentially have to calculate the ratio of pressure, total pressures between this point after the normal shock wave in each case and the total pressure of the upstream. Okay, and compare the two. This, I guess, hardest one of the bunch is problem part C of this. We are going to focus on this part C and go from there. So how does the part C look like? This is Mark 4 M14. We are also given P1 as 1 atmosphere. Then there's an oblique shock wave with the deflection angle of 25.3 degrees. What does deflection angle mean? We don't really have a surface here, but it essentially means that your flow is deflected by 25.3 degrees after the shock. Okay, so this is your theta. The shock angle is different though. Okay, and then let's call this beta of the shock angle 1. Then we have another oblique shock wave that is going to be met with the flow that is already deflected, right? Then there's another deflection angle of 20 degrees. And this will be met with a normal shock. Okay. So let's see how we should solve this. The first thing we want to do is to find the shock angle. How do we find the shock angle? Using the theta beta m relationship, or the graph that essentially graphs this relationship. So using the theta beta m relationship, we can find beta, or the graph, we can find beta to be 38.7 degrees. And the next step is to find the normal component of the flow, which is m1 sine of beta. Plug all of these in, you're going to get a value of 2.5. Okay. And then you can go to the normal shock tables for a Mach number of 2.5. We can find the total pressure ratio downstream and upstream, the shock to be 0.499. We have lost some total pressure. And the normal component after the shock is going to be 0.513. So this is region 1, region 2, region 3, region 4. Okay, so we have the normal component. We have the one of the pressure ratios. To find the pressure ratio after the second shock, we have to find the actual flow. So because this is the normal component of the flow, we have to find M2. And how do we find M2? It's M2N divided by sine of beta minus theta. You have all of these numbers, you plug the numbers in. M2 is going to be equal to 2.21. Okay, and 2.21. So add another page. So here M2 is 2.21, and it is met with a shock angle, with an oblique shock, with a deflection angle of 20 degrees. Sorry. What happened? Yep. Okay. 20 degrees. So we're going to take this M2, which is 2.21, and we are going to go to the beta theta m diagram, find beta 2 with this and a deflection angle of 20 degrees to be 47.3 degrees. Okay. What is the next step? To find the normal component, which is Mn2 is M2 sine of beta 2. It's going to give us 1.624. Take this number to the normal shock tables. We are going to get P03, P02. So the ratio downstream, the ratio of total pressure downstream the second shock with the upstream the second shock is going to be 0.887. and Mn and 3, so the normal component of the flow after the shock wave is going to be 0.6625. So we have our second pressure ratio. The first one was, I think, 0.499 after the first shock, after the second shock. And then we have another shock wave that is normal shock, which means that we have to find M3 using the angles and the normal component divided by sine of beta minus theta. Plug all of the numbers in, we're going to have 1.44 as M3. And then this M3 is met with a normal shock, which means that we can directly take this value to the normal shock tables, find 1.44. Of course, we don't have 1.44. You have to do an interpolation. Only one interpolation is required. The rest of these interpolations are not required, meaning that you can just do a guess what the value is. It has to be an educated guess, a good guess, but it can be a guess nonetheless. Take this value of 1.44 to the normal shock tables. So the total pressure ratio between downstream the third shock and upstream the third shock is going to be equal to 0.947. Okay. So what do we want? We want the total pressure loss between 4 and 1. And how do we do these calculations? We have the total pressure loss between 4 and 3 multiplied by the total pressure loss between 3 and 2, region 3 and region 2, and multiplied by the total pressure loss between region 2 and region 1, right? We have all of these values, multiply them together to come to a final value. I don't really have that final value here, but if you were told to find the total pressure at 4, you just had to go to the isentropic table to find PT1 divided by P1 as well, and multiply it by PT1, this whole thing, by P1, and then multiply by the static pressure, which is 1 atmosphere. Then you could have found the total pressure after 4, which is, I guess, something that is found in the solutions to be 63.68 atmospheres. And that's it. These are the example problems I wanted to solve. Again, to reiterate, you will be given, if you're an undergrad, you will be given 3 questions. If you're a graduate, you will be given 4 questions. Cheat sheets are allowed, 2-sided, one page, 2-sided, or 2 pages, 1 sheet of paper. And please let me know if you have a question. I will be in my office on Monday to respond to your questions and problems, and about the exam, about the project, about whatever. And if you finish your project early and want to meet with me in my office to present your work, that is completely acceptable. Just send me an email to schedule a time. I guess that's it. Good luck on your exam. And yeah, have a good day.